Chapter 1 Number System Part 2. Topic is irrational numbers. Irrational numbers is very interesting. The Pythagoreans in Greece, followers of the famous mathematician and philosopher Pythagoras. So his followers were called Pythagoreans, were the first to discover the numbers which are not rationals around 400 BC. So they discovered some numbers which were not rationals. As you all know that rational numbers can be expressed in the form P upon Q. Now they are discovering some numbers which cannot be expressed in the form P upon Q. It means they cannot be written in the form of a ratio of integers. There are many myths surrounding the discovery of irrational numbers by the Pythagoreans. Hipparchus or of Croton. In all the myths, Hipparchus had an unfortunate end, either for discovering root 2 is irrational or for disclosing the secret about root 2 to people outside the secret of Pythagorean sect. It is told that either Pythagoras drowned him to death, or it is even told that his shipmates drowned him to death when he discovered root 2 is an irrational number. In those days, it was like that. If you discover anything, they were just killed, like Socrates was killed. So this kind of customs prevailed in olden times. Let it go. But let's think about the irrational numbers. What are they? They cannot be expressed in the form of a ratio of integers. Now let us understand the formal definition of irrational numbers. A number S is called irrational if it cannot be written, mind well, it cannot be written in the form P by Q, where P and Q are integers and Q is not equal to 0. So an irrational number cannot be written in the form P by Q. There are infinitely many rational numbers. It means you can locate them on number line and there are infinite. So if rational numbers are infinite, then irrational numbers also should be infinite. So it turns out that there are infinitely many irrational numbers too. Some of the examples of irrational numbers are over here. Root 2, root 3, root 15. Pi is an irrational number. As you can see this decimal representation, it is non-repeating, non-recurring. What means non-repeating? Here you can see after 1, 1, 0. After that 0, you can see 2 ones, then 1, 0, then 3 ones. It means the number of ones is increasing. It is not repeating. So the zeros are repeating, but the number of 1 is increasing. Means it is non-repeating and non-recurring decimal representation. Nothing is similar in it. That is like non-recurring. So such decimal representation is called irrational number. Now what about root? Now root 4 is equal to 2. We have to assume such thing. We have to assume that positive square roots of the number are taken. Root 4 is equal to 2. Though we know that root 4 has two square roots. One positive root, a positive 2 and another negative 2. But we have to assume it as only positive 2. Now Pythagoreans proved that root 2 is irrational number. Then approximately 425 BC, Theodorus of Cyrene also showed that these all rational numbers which you are seeing on screen are also irrational. These all irrational numbers were discovered by whom? This Theodorus of Cyrene. Theodorus of Cyrene. Yes, children, here comes the bag full of rational numbers, which we have already discussed in the previous video. They are of the form P by Q, where P is an integer and Q is not equal to 0. Here you can see the integers 2 minus 125 in the form of numerators, which means P. Now here comes another bag with an arrow. Just guess what does this arrow carry? It's going to put some numbers inside this bag. Yes, you can see these examples we already saw in the previous slides. These are irrational numbers. Root 2, root 3, pi, 0.10, 110, 1110. This cluster of numbers will be put into the bag. What will be the symbol for irrational numbers? Yes, S is the symbol of irrational numbers. And now a third bag will come which will have all the numbers, rational, irrational, natural number, whole numbers. All sets of numbers will be together inside this bag. Here comes it, the arrow. And here are the set of all the numbers, right from natural numbers. You can see 1, -1 is an integer, 7 is a natural number, 9 is a natural number, -2 is an integer, 0 is our whole number, -7 upon 1, -7 upon 50 is a rational number, right? -7 upon 50 is rational number, root 2, root 17 are irrational numbers. So the cluster of all these numbers is called real numbers. The collection of all rational numbers and irrational numbers together make up what we call the collection of real numbers. Now, in this rational numbers, we already have the natural numbers, whole numbers, and every other number. Integers, natural number, and whole numbers. Now, this rational plus irrational makes it real numbers, and it is denoted by R. Therefore, a real number is either rational or irrational. We can say that every real number is represented by a unique point on the number line. Also, every point on the number line represents a unique real number. That is why we call the number line the real number line. So whenever we call a number line, it should be called as real number line because every point on that number line is the real number. As you can see, all these are real numbers. So any point will have any one of these numbers. So all the points are covered in real number system. It is this cluster of all the points, any point, may be a natural number, maybe a whole number, maybe a fraction, maybe a rational number, irrational number, any point on the number line will be one among this, nothing outside this. So the set of all the numbers on the number line is called real number. Therefore, it is a real number line. In the 1870s, two German mathematicians, Cantor and Dedekind, showed that corresponding to every real number, there is a point on the real number line. Just now we discussed that every point on the number line is a real number. And corresponding to every point on the number line, there exists the unique real number. So what does this unique real number mean? Unique means that point has a particular number which is unique to that point itself. No other point on the number line will have the same number. Each number is unique. For example, if we take a point as 2, then there is only one 2. There cannot be 2 or 3 2s. There can be another -2, means another integer -2. But 2 will not repeat on a real number line. That is called unique real number. Let us see how to locate root 2 on a number line. Now here you have to take A to B as a line segment equal to 1 unit. Now what does this 1 unit mean? Some confuse 1 unit means 1 centimeter. No. 1 unit can be 2 centimeters and I usually suggest you to take 2 centimeters. Otherwise, your representation will look very small and it won't be having good clarity. So, it's better you take AB as 2 centimeter. Now, if you have taken AB as 2 centimeter, you have to take BC also 2 centimeter. Same measurement. We have to draw a line segment AB of 2 centimeter. Then we will draw line segment BC of 2 centimeter. What will be the angle between AB line segment and line segment BC, it is going to be 90 degree. How to construct this 90 degree will be shown in the further slides. At present, just understand what type of triangle is being formed over here. Join the points A and C. Can you recognize the triangle formed? What type of triangle is it? Just guess and keep it in your mind. Here we are taking AB as one unit and BC as one unit. I asked you in the previous slide, what kind of triangle is it? If you had guessed it is a right angle triangle, then you are right, because AB is perpendicular to BC. Therefore, it's a right angle triangle, and we are going to apply Pythagoras property over here. Now, another question may arise to you that we had taken AB as 2 centimeters, then why are we writing 1 unit? So let me tell you that whatever measurement you take in AB, if you take 2 centimeter or 4 centimeter or 6 centimeter, ignoring your measurement, you have to only write 1 unit. AB as 1 unit and BC as 1 unit, because you want to locate root 2 on the number line. And you can get root 2 only if you are going to write these as 1 unit. Now on applying Pythagoras theorem, as AB is perpendicular to BC, AC squared is equal to AB squared plus BC squared. That is equal to 1 squared plus 1 squared. That is equal to 1 plus 1 is equal to 2. Taking square roots on both sides, AC is equal to root 2. Now this root 2 is located over here on the hypotenuse. So AC is the hypotenuse of this right triangle, and we got root 2 by applying Pythagoras theorem. Now we are going to locate root 2 on the number line. In the previous slide, we saw that AC is equal to root 2. AC is the hypotenuse of the right triangle ABC. But there is another interesting thing about AC. It is the radius of a circle with center A. So, AC is equal to root 2 is again a radius of a circle with center A. There is another radius of the circle with center A, that is AD. That means AC is equal to AD because both are radii of the circle. This is denoted by the red lines. These two red lines denote that both of them are equal because they are the radius of the circle with center A. Now, how can we locate root 2 on the number line? Join C and D. D is the point on the number line. The measurement of A to D is equal to root 2, which we obtain because both of them are radius of the circle. AC was already equal to root 2, therefore AD is also equal to root 2. The distance from A to D is equal to root 2. Once again, let me explain you that AC is equal to AD. Therefore, A to D is the measurement equal to root 2. Therefore, root 2 is the point D, denoted by point D, which denotes root 2 on the number line. Hence, root 2 is located on the number line by the point D. Now, let us learn the construction. Take a protractor. Mark a point at 90 degree. Here is the point at 90 degree. Now we will join the line segment and the point using a scale. Here we have joined the line segment and point using a scale. Then take a compass, put its pointed end at B of the right triangle ABC and put its pencil end at C. Make an arc at C with the pencil end. Make an arc at C with the pencil end. Remember that the pointed end was at B. Now join AC. Now join AC. AC is equal to root 2. With A as center and AC as radius, we are going to draw an arc and extend it up to the number line. Recollect what is the value of AC, what is the measurement of AC. It is equal to root 2. Why? Because it is the hypotenuse of the right angled triangle. Now extend an arc from C up to the number line. As you can see, with the pointed end at A and the pencil end at C, with radius AC is equal to root 2, we are going to extend the arc from C onto the number line. Now here I will put two questions for you. Where will the arc fall on the number line? At which point will it fall? And the second question is, what will be the distance A to the point on the number line? Let's see in the next slide. That the pencil end is falling on the number line at point D. The distance A to D is equal to root 2. Now, one more question. Are AC and AD equal, and if they are equal, then why? Yes, AC is equal to AD because both are the radius of the circle with center A. Thus, we located root 2 on the number line, which is at point D. Thank you.